We're continuing with the geometric sequence, and we're going to look at both the recursive and the explicit formulas again. So, recursive formula we saw, and when we talked about arithmetic, we were looking at defining the sequence in terms of the previous iteration. So, same idea here. What we said is a geometric is when we are repeatedly multiplying by a common term, a common ratio, I should say. So here's our recursive formula based on the previous iteration. We would just be multiplying it by that ratio. Again, just like we saw with arithmetic, we've got to define that for n being greater than or equal to 2, because we have to at least have had that prior iteration. Okay, so we're going to make our recursive formula here, so it's going to be dependent on the previous iteration. First thing we need is our ratio. So remember how we did that. We're going to take the second iteration, divide it by the first. Now, they've already told us it's geometric, so we don't have to check each of the iterations to see if we have the common ratio. We know we do. So our r is 1.5. So if we're looking for the recursive formula, it's easy. All we're going to do is take a sub n is going to be 1.5, that ratio, times a to the n minus 1. Or I keep saying it like it's an exponent. A subscript n minus 1. And we have to again define it for n being greater than or equal to 2. Now, in this section, I don't know why this is totally necessary, but they've been also just reiterating what is the first iteration. Okay, so let's make a recursive formula here. So what we need is our ratio. So what we're going to do is take the second iteration, divide it by the first. Now, if you divide a fraction by a number, the 2 is going to just multiply on the bottom. It really is keep, change, flip, but you're going to get 4/6 or 2/3. Okay, so we want a recursive formula, so a sub n is going to be our ratio, 2/3 times a n minus 1. Now, remember we're going to define that for n greater than or equal to 2. Oh yeah, and then again in this section they're defining that first iteration for us, just how to get it started. Okay, so now we're going to go explicit for this. The explicit formula, we saw this in the last video as well. But so the explicit is where we're going to define it without the previous iteration. We're going to do it based on the first iteration. So here's what we said before. This is what geometric is. You take that first term and you keep multiplying it by that common ratio over and over and over again. Well, that's what it means to multiply it by r to the n minus 1 power. We're just simply multiplying it by r repeatedly. Well, repeated multiplication is an exponent. Now notice here, it's starting with n minus 1 because we're going to start the iterations. N is going to be 1. Now we're going to have this issue too. So again, when we get to calculus, you can define it. N is often defined to start at 0 instead of 1. And we're going to see in the word problem here at the end, they do the same game where they've switched over to defining n equal to 0. But we should be consistent here for this. So we're going to stick with n being defined as 1. And because of that, then that first iteration, we need to not multiply by anything. We need to multiply it by 1. So this is the reason, because we're starting with n equals 1, that's why r is going to need to go to the n minus 1 for our formula. But I'll talk more about that as we work with some of these. Okay, so we need the explicit formula for the geometric sequence. So we have our first term. What we need to do is they want us to find our second. Well, we don't have the ratio. So what we're going to need to do is we're going to need to use our formula here. So we're going to do a to the 4th would be 3, that initial term, times r to the 4 minus 1. We're looking for the 4th term, so our r is 4 minus 1, or r to the 3rd. Okay, now if we just solve this, so we've got our 4th iteration, that makes r to be to the 4 minus 1, or the 3rd power. We can solve this for r, and we get our common ratio is 2. Alright, well if we know our common ratio and we want to find the second iteration, well all we have to do is multiply the first iteration by 2, and we've got it. It would be 6. Okay, now this is going to be a little different here because we don't have the first iteration. So what we're going to do here is an a2 going to be equal to So what we're going to do is a series of equations again. We did this similar idea when we were doing arithmetic. So we're looking for the third iteration here. It would be, r to the 3 minus 1 is how I should have done that. Okay, now we have some of these values. So I know 4 equals a1 r to the first, and I know a3 is 32 a1 r to the second. Now, I can use a system of equations approach to solve this. So I'm trying to see which would be easier. Yeah, well, let's solve. Okay, so let's go this way. So we want a1 is then going to be 4 divided by r. So let's take that and we're going to plug it in here into the second equation. 32 equals 4 over r times r squared. Well, this is pretty easy here. So we've got the r's, one of the r's will cancel. So I can cancel this r with the exponent. So this get down to 1r, so I've got 4r. Now I'm going to swing this around just because I'm running out of space here. I don't like to work it that way. Okay. Okay, so if I divide this by 4, I've got r is 8. Now I have r. I can find the first iteration. a1 equals 4 divided by 8, or 1/2. Okay, now I have everything I need. So our explicit formula would be a sub n equals, well, let's do this, a1 r to the n minus 1. But I have r and I have a1 now, so an is going to be 1/2. My r is going to be 8, and I'm doing it to the n minus 1. Okay, let's find a6. So the sixth iteration is going to be 1/2 8 to the 6 minus 1 power, or 5. Okay, so let's crunch this. I'm going to let the answer here. So it turns out to be 16,384. We do 8 to the 5th. Remember, order of operations. Please excuse my dear Aunt Sally. We got to do exponents first. 8 to the 5th, and then divide that answer, or multiply it by 1/2. And there we go. Okay, so now they're going to ask us to find, oh no, we're just finding the explicit formula again. Okay, so the only difference here is we don't have our common ratio, or we can do it, actually this is easier than the one we just did. Take the second iteration divided by the first, and we've got our ratio. So r is 5. So a sub n is a1, r is now 5 to the n minus 1. And we know a1 is 2, and that's all we need. Now, we should, well, they didn't do it, but we should have said, whoops, for n greater than or equal to 2. Okay, let's write an explicit formula for this sequence. What we need is that ratio. So we're going to take the second iteration divided by the first, and our ratio is going to be -3. So this is easy. a1r to the n minus 1. Well, if my first iteration is -1, I know r is -3, then I've got it. Now again, I'll say for n greater than or equal to 2. So all I had to do was find r. They told me a1, so that was nice and easy. Okay, we're going to end with a couple word problems, and just like I noticed they did in the arithmetic sequence, they're going to mess with us a little bit. They're changing their formula again to start with n being equal to 0 for the initial. There's nothing wrong with it. It's perfectly fine, but they haven't been doing that consistently. So what they're saying here is they're going to start with this initial amount as 284, and then we're increasing by 4%. Now we saw this previously when we did exponential functions. If you're increasing by 4%, that means your rate here is 1.04. So that's how much we're increasing. You've got to remember 1 is the base. You have to have a minimum of 1 or else you'd be decreasing. So we're taking our initial amount, multiplying it by 1.04. Now, they did n. So this is where they're starting with an n as being 0. If their initial amount is 284 and they put n as 0, well then they get 284. But if you think of it like the way we've been doing, where the first iteration is 1, then what we would have done was 284 times 1.04 n minus 1. Now, it's a semantics thing, so you can do it either way, but if I think of the first iteration as 284, then I need to use this. What they've done here is they thought of n as being 0. So, but to be consistent with what we've done, we would use n minus 1. So there's our formula. Now, it is 7 years between 2013 when this started and 2020. So they want us to tell what the population would be. Well, this matters whether you're using n as 0 or n as 1. If you're using n as 1, 7 years later is going to be the 8th iteration. So if we're using this formula, which I think we should, we're using the 8th iteration here, which would then make it 284, 1.04, 8 minus 1, or to the 7th. So that then gives us the same thing as then, but again, they started with n being 0. So what I'm doing here is I'm using the consistent formula that we used. If you use 7 years later, you're at the 8th iteration. So crunch this, we get about 374. Okay, so we're going to do the same thing here. So we're starting with 293. We're increasing by 2.6%, so we've got a 1.026. We're going to make that a decimal, but 1 has got to be the baseline or else you're decreasing. So we're going above 1 if we're going to use an exponential here, and then we're going to do n minus 1. Okay, so here's my formula. We're going to call this a sub n. So there's my formula. Now, how about the number of hits in week 5? Now, I was again confused by this, but they're meaning a sub 6. That's what they're saying. So initial is a1, which is what we've got here, and then we're wanting 5 weeks later, so that's a6. So that's going to be 293, 1.026 to the 6 minus 1, or to the 5th power. Crunch that down, and you're going to get 333. Okay, there's the geometric sequence. I think we're going to look at that again in the next section, but hopefully so far this has been pretty self-explanatory.